mentioned. This is specifically on Cloud Burst Compute. I'm going to touch a little bit on two areas. First, kind of explain what the business side of it might be. Very quickly, don't want to bore you too much. I know most of us here are technical. And then from there, go into kind of the technical, do a very high-level overview of what it looks like. And then from there, we'll kind of dive into the different products and actually play around with it a little bit. So we might as well get started. Okay, so Cloud Burst Compute, specifically a new thing that's been developed by Ansys, available to everyone as of 2025 R1. The main reason for it coming up is due to market trends, right? So as with most products and things that we develop as we go, there's been three main pillars when it comes to market trends in terms of issues that we've recognized, and those come down to just kind of computational ability. We all know that we can set up relatively complex simulations nowadays with some sort of ease from a pre-post point of view, but once we send it to the solver, some simulations might cause us to sit for a matter of days, especially if you're in the DEM space. There is a bit of unfortunate there, but we'll get into that in a little bit later on. But generally, we often lack the ability to go ahead and compute our simulations from a heavy hardware resource point of view. So definitely have limited computational capacity, especially in South Africa where H100s or A100s cost an arm and a leg. Another thing that's massive is just RT resource and expertise. The RT expertise is a big one, right? As much as we're engineers and we are relatively smart beings, it is quite a difficult thing to learn on the fly how to set up a whole RT system for a cloud or an on-site cluster that would go ahead and essentially run your simulations. And then lastly, one of the major issues, especially with all the consulting companies in South Africa, is that sometimes we don't always need a solution that's going to last for the next 5 years. Sometimes we're running a project that's going to be running for the next 3 months. And so we need some sort of computational capability or capacity in those 3 months. And hence, we don't have the need to buy or spend lots of money on all of that hardware to run our simulations for that long time. And this kind of leads us to where Cloud Burst comes into the picture. So with Cloud Burst, we essentially mitigate the three pillars in terms of the problems, right? So we have HPC on demand. So all this means essentially is that if we need more computational capacity, we can get it as we need it. That's a very big thing. There's no RT setup, so this is off-site cloud in terms of computation, where we will essentially be uploading our simulations, letting them run on cloud infrastructure set up by Ansys, and not have to worry about the RT side of it, so not have to worry about setting up domains or infrastructure or even the software side of it. That's already all set up. And then another really good feature is that we pay for what we use. So if any of you have ever looked into elastic currency, Ansys's elastic unit, for examples, you'll see that this is a very similar setup where you will essentially buy a certain amount of credits. These, maybe it's important to mention that these aren't the same as the elastic currency. Cloud Burst Compute will have its own currency called Ansys credits, and those will be used essentially to solve with. But essentially, you will buy a whole bunch of them up front, and then as you simulate, you will use up your credits. And then it is on a top-up basis. In terms of the cost and everything, you'll have to contact your salesperson. But essentially, if you've run out of units, you can just go ahead and load more on, top up your account, and then carry on simulating from there. So that's kind of the business case for Ansys Cloud Burst, right? but we're probably today a little bit more interested in the technicals. So what can we currently use, or what products can we currently use Cloud Burst for? Where can we take advantage of it? Everything on the screen essentially. So Mechanical, Electronics Desktop, Fluent, Discovery, and Numerical at the moment. These are the current supported Cloud Burst compute products. Again, as I mentioned, if you are in the space of discrete element modeling, unfortunately, we aren't there yet. But these are already a great start in terms of what we can do. Each of them require a similar setup where we're just going to sign in. I'll show you a little bit on that now, so it's not super complex. The only one that's kind of different is on the discovery side, but we'll jump into that with the playing around live, if I can put it that way. Don't really want to call it a demo. Anyway, how to set it up. This is taken from Mechanical, but as I mentioned, across most platforms, it should be very similar. Essentially, where we have our solver process settings, we're going to go ahead and add a queue. So you'll see essentially I'm adding another queue to my list over here. Once I click on add a queue, this little window will pop up. You'll see I just name my process. And then from there, we can go and choose our Ansys Cloud Burst compute as an option. From there, it will ask us to sign in. You can see I have already signed in. Unfortunately, it's not showing my password. Otherwise, everybody would have been able to have a field there. We can also then go ahead and set our account. This is usually going to fall under your company's domain, but there is place to kind of set it up individually for each engineer. Again, you might just have to consult your salesperson with regards to if that means double costing or not. But you can definitely link it to a single person or a company account if you'd like. You can see my credit balance is 0. That's because this is linked to my current email. If I change it over to the company, you'll see our credits will display. I'll show you that a little bit later on. And then from there, we have a few advanced options that we can follow. So essentially, we can go into our advanced options. We can set our cluster. So you can see that's what I've done here. Over here, I've gone ahead and set that I want a machine with 64 cores. And then from there, it's just running it as normal. So from there, we go into Mechanical. Again, some products might look slightly different, but I go and choose my remote server. I would click solve, and then from there, it goes ahead and solves. Don't worry about some of the red. It just means I haven't downloaded my results yet, but I'll show you what that looks like in a bit. Then from there, once we've clicked solve, we'll essentially need to monitor our processes in the engineering portal. Right. So our engineering portal shows us a few different things. We can see things like what products we have. So here you can see we've got Cloud Burst Compute, and then we also have our products, our projects, and our studies. So essentially what this shows, or those little folders, I'm going to show you what they all do now, but essentially they're just our little buckets where we go and organize our projects as we move through each one. So in our products, just shows our products, similar to our homepage there. This one's nothing special. But our projects, this is now where we can go and create projects. This is useful for if there's multiple of you in the company who are busy trying to run simulations on the cloud, then you can go ahead and set up kind of like your own folders. You do get a certain amount of space assigned to your account. I think the base, the base or the standard is 1 terabyte worth of space. So just keep that in mind. Again, consult with your salesperson. Just ask them questions about how much space you get and how many credits you get up front. Then from there, we can have a look at our studies. As you can see, I've been playing around with it quite a bit, having lots of fun. We can see quite a lot of metrics. You can see how many credits I've consumed. We should at some point be able to see what our full credits are or how many credits we have left. And then from there, if I dive into a specific, let's say I click on a specific study, I get all the output files of my simulation. So what's cool is before even downloading, if I want to double check that things are going okay, and while it's simulating, I can monitor these files while it's running or after it's completed. You can see I had a successful run, which I was very happy about. And I can then go and look and analyze my solve out, for example, which prints out the exact same solve as you would see in Mechanical, for example, if you were to click under Solution Output. One big question that I think a lot of people ask is, what about my licenses? Licenses are quite cool, or it's quite a cool thing with cloud. Cloud Burst is not a bring your own license solution. What does this mean? Essentially, and I'll show it to you in real time in a little bit. Essentially, if I open Mechanical app and I start a cloud run, if I close my Mechanical instance, this solution will still run in the background. It's because I've now gone and put it on the cloud. It runs with its own licenses on the cloud. So essentially, cloud is like having its own licenses. We can queue a bunch of runs. So essentially, what's nice about this is I can send my simulation to the cloud, and then kind of open another instance of Mechanical and start setting up my next simulation, and possibly solve locally as well if it's a different simulation, a different instance. So this is by far the coolest part about it. Again, take that into consideration when you see pricing. It's not going to pull your current licenses. It uses its own licenses in the cloud. That's part of your credits essentially, which makes this quite a powerful solution for getting a lot of simulations out there. Or if you just want to run one simulation that you know is going to take a while, while still keeping your licenses for other uses, for example. I essentially alluded to in the slide. So in this case over here, let me just disconnect this here. You can tell I was playing around a bit early on. So essentially we've got quite a complicated setup. In this case, we're looking specifically at a nonlinear adaptive simulation. So essentially we've got like a rubber boot or rubber seal that I'm going to be squeezing into this little gap, right? Something that typically takes quite long, requires a lot of iterations. In this case, it's an axisymmetric simulation, so there isn't really a need for cloud in this case. I'm going to show you a little bit more about when there is a need in a bit, but this is more for showing you the process. So again, we simply go over to this little button over here below our solve. We wait for Mechanical. Once we've clicked it, we wait for Mechanical to stop throwing a fit, and then from there we can go and set up our remote server. So in this case, I'm just going to do the same process again. I just add queue. We give it a second to load. Sorry, there might be a little bit of white space in between each thing I click, just to give Mechanical a bit of time to load. This is loaded now, so all I'm going to do is, instead of going for HPC or RSM, I'm going to just select Ansys Cloud. I'm going to make sure it's on the account that actually has credit. You can see I can see my available credits within the Mechanical interface. I don't need to go to the website to see that. And then from there, I can go ahead and set up my advanced properties. So in this case, I'm just going to grab the only cluster there is available to me at the moment. And this is where the real magic comes on. So essentially, over here, I'm choosing how many cores it's got. And then the number next to it is how much RAM I have based off of that. And you can see this guy's quite a beefy one. The AMD below it is even better. I just tend to gravitate towards Intel more. So essentially, I'm going to choose 64 cores on 1024 gigs of RAM. We can play around further if we really want to. We can go and set up our threads or number of processors. We can go and specify how many CPUs we want per node. So in this case, for example, if I choose this cluster only has 32 core computers, and I want 64 cores with 1024 gigs of RAM, this is essentially going to grab 2 nodes for me, right? So just leaving it on default means that it will automatically. But if I wanted to split this up over a couple computers for whatever reason, I can go do that, right? So if I have GPU acceleration on for Mechanical, I can also go set that up. We can specify memory and disk space requirements. This comes in for if we're looking at kind of saving space with regards to our accessible cloud space that comes with your credits. And then from there, we can go and specify additional files if we need to. I don't need to right now, so I'm just going to click OK. I'm just going to click OK again. Now that this is set up, I can go over here, and you can see I've got all my options. Now that I've got resources, I don't want to use my computer anymore because that's for outdated people. And essentially, it's the same as just running any other simulation. Once I've set it to cloud, I don't need to worry about cores. I'm lying to you, I do need to worry about cores. I want to set 128. So this will grab two nodes of 64 cores based off of what I said set earlier on. Once I click solve, this is where the magic starts. So maybe I can talk a little bit more just about the process going forward. So from here, Ansys or Mechanical is going to recognize that I've chosen the cloud as my solver. From there, it's gonna say, okay, in order for it to simulate, it needs the files. So you'll see over here at the moment, it's uploading files. This is essentially uploading my simulation, right? It's also important to note that you'll see mesh that had to have run first. So we still have to generate our mesh locally, at least in Mechanical. This won't be generated in the cloud space. We're only focused on solution when it comes to the cloud solving. So you see it's uploading the content. This is now going to be relatively heavily dependent on your line speed. So because we are talking to the cloud, internet is your internet does need to be fast if you want the upload cycle to be quick. However, we're not really worried about the upload. We're more worried about the computational capacity. But obviously keep in mind that if you're running on a 1 megabit line, obviously it's going to take a little while to upload your stuff, and then you've got to beg the question of whether the upload is worth the computational capacity that you're going to gain. Nowadays, though, these things happen quite quickly. This is sending it to a server in the Americas. As far as I understand it, there aren't servers yet in the EMEA space, but that is something that might come in future. Okay, so we'll see that the remote's starting up. Once that's started up, we can jump back into our portal over here. We can jump into our projects. So this luckily automatically sees the name of my my workbench. That is on the other screen over here. You'll see I've got it as NoLinProb, short for nonlinear problem, because I'm lazy when I type. And then once this is uploaded, we'll see. Might just need a second to think. But essentially, once this is uploaded, we'll see it on the engineering portal side. First time I ran this, I got a fright because my process bar disappeared, right? Which is scary because if you've run into a screen that looks similar to this before, where it's solving, but it's not really solving, you know that your files are possibly corrupted. When we solve on cloud, it's definitely not the case. This is essentially just telling me that my simulation has been uploaded, and it's now currently either queued or it will be simulating. So how we know that is I can stop, but mainly we're going to click on job status. Let me just click on that to show you. But it essentially just opens up my my engineering portal. Takes a while to load, and you'll see now I've got a queued simulation. This does take a couple minutes to simulate, but the nice thing here is that this is the cloud service is available 24/7. So once it's queued and you're relatively confident in your setup, it will go ahead and simulate as it needs to when once the queue is or once it's come off of queue. The queue, I think, is actually just at the moment more of a pre-check to make sure that the simulation will run at least. It won't be able to tell you if it's going to fail or not, unfortunately, but that seems to be what the queue reason is. Also, if there are obviously not any resources available, it will wait and put you in the queue for when resources do become available. But again, this has been a few minutes at least. Okay. Once this has run, I'll be able to download the files. And so I have another simulation set up just to iterate that. Oh gosh, maybe I don't have one set up. Open this up again. This is essentially, I went and let's just see if this will show. Don't think it will. Ah, there we go. Okay, so essentially I just played around. If any of you have done training, training with us, mechanical training specifically, you would have come into contact with this model before. This is the sub modeling, the sub modeling workshop. Essentially, I took this and I just gave it the exact same parameters. So it's a relatively linear problem. We have frictionless and a compression only support at the bottom. So there is one non-linearity essentially. But I went to mesh the hell out of it. So at the moment, if I can show you here, we're essentially sitting on 2.6 million nodes, way more than I need for this problem, understandably. But we're testing here. We're not too worried. So essentially, we ran this in the cloud, and for the 2.6 million nodes on 128 cores, it ran for 9 minutes 43 seconds. That's from the start of the simulation in this environment. This doesn't include the upload time or the waiting for the queue. And in terms of this guy over here that we're busy running at the moment, let's just see if it loads our solution information. You might just have to believe me if it doesn't load, but essentially I started this at about 12 minutes to 1 to kind of drive home my point. Okay, Mechanical's not listening to me at the moment. Just give it a second. Okay, there we go. Let me see if it shows me at the top here what time we started. Should show me on my iterations. It is not. I'll have to send a screenshot through on the chat once it's done running, so that we can see what time it started and how long it's been taking. But for now, in the webinar, you'll just have to believe that it was started before 12, sorry. Okay, then, so that covers mechanical. I hope you've written down your questions in case you have some on mechanical, because I'm going to switch over to discovery now. Discovery, we have a slightly quicker process when it comes to cloud compute, slightly more involved process, but also, as all of you know, discovery has got quite a lot of different. It's multifaceted. I think that's a better word. So essentially, I've done all the boring side of it already and gone and set up a problem. It's essentially just a heatsink with a little silicon chip at the bottom that's generating 10 watts of heat essentially. And I want to know now, or I want to do kind of, we'll call it a parametric study. I want to know how many fins, or whether having more fins would help, whether having thinner fins, that's a tongue twister, or thicker fins would help me in any way, or whether extending the length of this heatsink is going to help me in any way. So I've done all the boring work. I've put the geometry in. I've assigned materials already. I've gone and put my convection in. I've added heat. And so essentially now we want to set up a parameter study. So at the moment, my parameters are fin count. So you'll see if I click on this guy over here, I've parameterized how many fins there are. This is just essentially a pattern that is on here. I've parameterized fin width. This parameter, which I have not named, is essentially just the length of the heatsink, and then this parameter is just ensuring that the fins keep their length relative to the base of the heat shrink. Then from there, we go over into variations. You can click define variations. I used a manual setup and then decided how many variations I wanted and what my start and end values and intervals was. If you use the Latin hypercube, it kind of just sets this up for you automatically, but you are capped at 100 variations. Then from there, I can go ahead and see all of my parameters or my different design points, if you want to call them that rather. So you can see I've got 6 fins, and then it tests at the different widths and lengths, and then I've got 7 fins and 8 fins, for example. I think this goes all the way down to 14. Yeah. And then from there, we can now go ahead and run the actual study. So I'm just going to make this its own little window, so it's out of our face. I'm also going to pop our little defined variations graph up here. See if I can't grab this to make it a bit smaller. Okay, so I've already had some of them run, but what I'm going to do is I'm just going to start this from scratch so that you guys can see the process. In Discovery, it's super easy, right? We click on our update button over here. We just click on the drop down. I can choose to do it locally, or I can choose to do it on the cloud. Once I select the cloud option and I select update, it will prompt me to log in. It'll tell me an estimation of how many credits I'm going to use, and then from there we can simulate once we're logged in. So I'm just going to say update all. Should kill my my current results already. Here we go. So I set my count. I see how many credits I've got. I can see how many credits this is going to cost, which, by the way, is quite crazy. 60.63 credits. I think a credit is $1. Don't quote me on that. But 0.63 credits essentially, and that's going to do 160 something variations. So if I go submit. The one thing, again, that stunts us here is upload time. So it will take a while to upload, and that's what our little different icons here are essentially. So this is uploading. This means that it's queued. This means that it's solved. Essentially, this one I think is that it's running. There we go. This one has warnings or out of date, and then this is not solved, for example. So we don't want to see a lot of those. And so you'll see as it goes ahead and updates my design points and uploads them, it's going to start changing my geometry based on my parameters that I had set up. So at the moment, it's first going to play with the length, and then it will play with the thicknesses, and then it will start adding more on for us. There we go. Once it started solving, which hopefully it does the first one soon. It should start going soon. We can then click on a specific solution, make it active, and then plot the results as well to see what our actual temperature distribution is. So in terms of Discovery, quite a powerful tool from a point of view of kind of parameter study. We can't do topology optimization just yet in terms of the mechanical space with cloud solutions, or from the CFD point of view. But in Discovery we can kind of make up for it a little bit. So you can see now it started to solve. We've got this guy going, and then eventually this should refresh. Maybe let's click on that guy. It should refresh once it starts solving, and it should start plotting all of our options. And you can see the general trend just based off of what I ran earlier is that more fins kind of directly correlating to less max temperature, which makes sense from an engineering point of view. And so yeah, I hope that kind of gives I'm just going to stop this. That kind of gives a good overview of what you can expect from Ansys Cloud. I know it's more specifically on the mechanical and Discovery point of view, but should nonetheless carry the point over, hopefully. Let me just show you this quick. So we've run this variation. Well, I guess let's not show you this one because this is the original. So we just show this one, for example. Make this our current variation. I should update my geometry. There we go. Then I can click solve. Can put that on, and then it will run. I can interrogate each design point individually if I would like.